In this Google Colab, you will see some of the code. So I make it simple at this time. So maybe next week we will look at more complex code. Okay. So the first is it is about the one-hot encoding. So in this one-hot encoding, in this code, it is the one-hot encoding from the corpus. Usually we call corpus as the collection of sentences. So here we have 3 sentences, like you see in the PowerPoint. We have I love this movie is terrible movie, the plot is confusing. Okay. And we use the count factorizer to make the factor. And as you know, we can make based on the frequency, or we can make as a binary. So if it is binary, then we call this is the one-hot encoding. So this count factorized is binary true. So we can make the one-hot encoded based on this factor by using the fit transform. So fit transform of the vector from the corpus, from this one, and then we can get the feature names is this one. So we can get the one-hot encoding like this one. If we use the back of words, so we can remove the binary equals to true. So binary equals to true, yeah, it works for the one-hot encoding. But if it is the frequency, we can just put as the method for the count factorizer, and then we again fit transform to the corpus. So if you look at this one, then this is the factor from back outward. If we use the TF-IDF, we can use the TF-IDF factorizer from the sklearn, and we just fit transform the corpus based on the TF-IDF factorizer, and then get the features name out. It means this is the features, and then we can have the encoded result like this one. So this is the first document, this is the second document, and this is the third document. And this is an example of the n-grams. So you see the n-grams. Let's say this is a function. You can give the sentence comma n means the number of items that you want to analyze. So the word will be split from the sentence, and then the n-grams, it means we are going to merge. Okay? We are going to merge from the n items. So we use the function zip, and we are going to look at the words from the I until the n, when the I is in the range of n. So I hope that you can understand this one. For it is a for loop from I until the n, and then for every word from I until the n will be zip or will be merged. And then at the end we will make the list from this n-grams. So if you see this one, the sentence is 안녕하세요. 만나서 진심으로 반가워요. Then if it is a unigram, I want to know the n-gram sentence 1. If it is bigram, we want to know the n-gram sentence 2. If it is a trigram, we can use the n-gram sentence with the n equals to 3. So the unigram means the word only one, word is only one, the word is only one, the word is only one. If it is bigram, there are two words, two words, and if it is trigram, there are three words. There are three words. We can use the NLTK. NLTK is the library, the natural language toolkit library, and we can use the n-gram. The n-grams is method, and we can just directly split the sentence, and we just put the item. So we can also use this one, and the result is the same like this. Okay. So let me continue with the other methods. We call it as the distributed base method. So in the word representation, or yeah, we can use the word like text representation. As you might know that the word representation require a discrete symbol. The discrete symbol, yeah, we can use numbers to indicate something that the word exists. So we already know if it is the one hot factor, so we can look at, yeah, this is a cat, so we can make like this, is 1 and the other is 0, is 1, the other is 0, this is 1, the other is 0, and then cat, this is 0, 1, 0, 0. If you want to represent with this mechanism, with this method, with this discrete symbol, yeah, we have a factor dimension, and if we want to measure with all the vocabulary, it is very huge. Why it is very huge? Because in the vocabulary, we will have about like 500,000 vocabulary. So you can imagine the number of columns will be 500,000. So we want to make something meaningful words. The meaningful words means, yeah, we are going to make a kind of factor model by focusing on the similarity. So each word is regarded as a factor. It is different with the previous one. In the previous one, we have the factor is a document. So one row means one document. Now we can make the word representation where the words as factors. So if we look at this word, the word apricot, it is a factor. And then when the word apricot appears, I want to know how many other words appears at the same time with apricot. So similar words are nearby in space. So the first solution is we can just use context factors to represent the meaning of words. We call this is the word-to-word co-occurrence matrix. Okay, what does it mean by word-to-word co-occurrence matrix? Let's say this one. I want to know the word apricot and how many times this word appears together with artwork. Do you know artwork? It is a kind of animal. So let me R dot. This is R dot. This is an animal. So I want to know whether the word apricot appears with alpha. Okay, 0. So means nothing. There is no document that show apricot with alpha. Apricot with computer, 0. Apricot with data. Apricot with pins. Okay, there is 1. Apricot with result is 0. Apricot with sugar, 1. Okay, I hope you know what is apricot. Do you know apricot? Apricot is a fruit. Apricot. Also, okay. So we call this is apricot. Okay, we know that apricot there is no connection with computer. There is no correlation with data. Pineapple, the same is a fruit. So there is no word with alpha. There is no word of pineapple with computer. There is no word of pineapple with data. But there is a word with pins and there is a word with sugar. The same with the other word like digital and information. The word digital, we have 0 with alpha, but okay, there are 2 appears together with computer. And the word digital, there are 1 appears together with data. And there is 1 appears together with result. The same with the information. We have 1 for the computer and 6 on the data and 4 on the result. So this we call as the word co-occurrence matrix. With this word co-occurrence matrix, we can make a kind of graph. So this is the graph from the previous co-occurrence matrix. I want to know if I have the word result and I have the word data. So how many times if we want to look at the word digital? Look at this one. The word digital. The word digital, it shows that there is 1 with data and 1 with result. And the word information, we have 6 on the data and 4 on the result. It means we can find like this one. The digital is 1 on the data and 1 on the result. And the word information, we have 6 on the data and then 4 on the result. So this is the location and this is the location. And if we use these words as factors, then we can calculate the similarity. So if you still remember when you learn in data mining, I think I'm going to discuss more about the cosine similarity. Okay. So we can use the cosine similarity to look at how close the word digital and information from the respective of the word result and the word data. So you can have this one. 6 multiplied by 1 or multiplied by 1 and so on. So we can look at the similarity based on the distance. But the problem is, not all counts are equal. So if it equals, then we can say, okay, the word is similar. And the words can randomly co-occur. So you can see from this one, this is fruit. And this is about technology. So the word can be random. And when we do with the similarity, of course, it is the result will be also a kind of random. So we need to kind of finding the weight, or we call it re-weight, by how likely it is for the two words to co-occur by simple chance. So we have the PPMI, or we call it, this is the positive point-wise mutual information. So the PPMI of the word, comma, co-occurrence, okay, or the count of the co-occurring, it is the maximum of the log, comma 0. What does it mean? So if this log, the result is negative, if the result is negative, then we will not choose this one. We will choose the maximum between the log and 0. So if it is negative, then we will put as 0. If it is positive, then we will choose the log result. So the PMI, we can have this log probability. We have the PW, C. This is the probability of W and C co-occurring divided by the probability of W occurring and the probability of C occurring. To make it simple, maybe the formula is not that simple, but I think it's not that difficult to understand. The matrix F with W rows or words and C the columns, this is the context. So we will use this data. So the Fij is the number of times the Wi occurs in the context J, Cj. So I want to have the Pij. It means how many times the word I appears in the context J divided by the summation. We have Pi star. Pi star means the total of the occurrence of the I and J. And then we want to know the occurrence of only the J. The star means all J. P star J. So it means I want to know the occurrence of all I divided by the total frequency. So we have the PMI like this one, the same formula like the previous one. If it is positive, if it is higher than 0, then we select the PMI. If it is not, then we select 0. So that's the meaning by the previous example, the previous formula. Now let's see with example. I want to know what is the factors of the words when we have this frequency or the count. Let's look at this example. We want to know the probability of the W information given in a context when C equals to data. We want to know the information in the context of data. So we have 6. Okay. We have 6 out of 19. What is 19? 19 is the number of words that we have in this matrix. So if you sum all those 1 plus 1 plus 1 plus 1 plus 2 plus 1 plus 1 plus 1 plus 6 and plus 4, so the total will be 19. So we have the P when the word is information and the context is data is 0.32. So we have 0.32. And then we will have the probability where the word is information. Where the word is information is there are 1 plus 6 plus 4. So it means we have 11 divided by 19. 19 is the total from the co-occurrence matrix. And we want to know the probability of the context word or the column, which is data. So we have 7 out of 19. Okay. So after this one, so we can calculate the PMI. What is the PMI? The PMI is log of the 6 divided by 19 divided by the probability of the word information, which is 11 divided by 19 multiplied by the probability of the data, right? By the 7 divided by 19. So we will look at this one, whether it is positive or not. So we have this information. This is the co-occurrence matrix. And we want to see the word cherry. How many times it appears with the word computers, data, result, pie, and sugar. The word strawberry, how many times it appears with computer, data, result, pie, and sugar. How many times the digital and information. So you can see with this frequency. Now, if you look at the digital and information, you can see some numbers. So, why does the word cherry and computers become zero? So this is the PMI result. Okay. So this is the PPMI, the positive probability mutual information. Some of them equals to 0, even though it shows a number or there is a frequency. So if you calculate this one, you can do the summation for all of them. Okay. So it means 2 divided by the total of this one. So the total is about the total is about 11,716. Okay, so you can calculate with your calculator later. And then we want to know the number of the word cherry. The number of the word cherry, there are 486. So later you can calculate. And the word computer, there are 4,997. And if you do with the PPMI, so it means 2 divided by 11,000 something, and then we will divide with the 486 divided by 11 4,716 multiplied by 4,997 divided by 11,716, and then you can do the log. And if you look at the log of this one, the result is negative. Why it is negative? Because this number is very low. So the low frequency will have a negative result. And as we know, the PPMI, what is PPMI? PMI is the positive pointwise mutual information. So we want to check the maximum. If the log is negative, then we will select 0. So later you can calculate by yourself. This one 0 because the log result is negative. Then this becomes 0. This becomes 0. This becomes 0. So the word co-occurrence, it is the starting point when we want to make another representation. There is another representation, we call it as a skip-gram. So the skip-gram is the word-to-fact architecture. Okay, we call it the word-to-fact. It is word as a factor, word-to-factor. We call it word-to-factor, which the input is the center word. So the input is the word, and the predictions are the context words. So let's say the context here is a fixed windows of size 2m. 2m means 2 window. So if I want to make this as the center word, into, what is the word before into? What is the 2 words before into? So we call this is word t minus 2. This is word t minus 1. And we have the word after into, and we have the next 2 words after into. So we call this is w t plus 1. This is w t plus 2. So WT means the word at the current time. So given this center word at a position T, and I want to know what are the most probable word in the T minus 2, T minus 1, T plus 1, and T plus 2. So we can also do with the other one, for example, banking. So we want to check what is the t minus 1, what is the t minus 2, and what is the t plus 1, and what is t plus 2, and so on. Okay. So this is the concept of the skip-gram. So given a word, question is, can we predict its neighboring words in a text corpus? So if I have the WT, the current word, can we predict, let's say, if we use the 5-gram model, so it means I can know the 5 consecutive words. So if I have the center word, WT, then I want to know the WT minus 2, WT minus 1, WT plus 1, and WT plus 2. So this is the concept of skip-gram. So this is an example. Okay. Let's say I have the word New England Patriots win 14 straight regular season game at home in Gillette Stadium. So using the skip-gram, let's say I want to put this patriots as the sentence, as the center word. So as the center word, I want to know what is t minus 1, what is t minus 2, what is t plus 1, and what is t plus 2. So as the input, the word patriot with the one dot encoding, we can use the patriot is this one at this time. And then we will do with the neural network. So I will not explain the neural network here, but the result will be the probability when the word new, the probability when the word England, the probability when the word win, and the probability with the word fortune. Okay. So this is the formula. We can use the log function to look at. So this is the probability that the word t plus j given by the word at the possibility. There is another kind of representation, we call it CBOW, or continuous back of words. The CBOW, it is also a word to fact architecture that predicts a target word based on the context word within a fixed window size. So different with the skipgram, if in the skipgram you will have those center word, and then you will predict what is the t minus 1, t minus 2, t plus 1, and t plus 2. For the continuous backward word, we will give the context. The context means any words in the t minus 2, any words in the t minus 1, in the words in the t plus 1, and the word in t plus 2. And the output, we would like to know what is the possible word in the time view. So for example, if we have C is a blank tensor. So what is the possible word in this position? So we can predict, for example, it is word green. So if you can see, the architecture will be the same, but the result and the input is different. If the skipgram, the input is 1 and the output will be some possible words in the t minus 2, t minus 1, t plus 1, t plus 2, depending on the grams. But the CBOW, it uses the multiple inputs and we will predict on demand. So with the same idea, like this word, New England Patriots win 14 straight regular season game at home in Gillette Stadium. So we will give the context. So New England win 14. So we have New England win 14. So after we make it as the text representation, when we fit into the neural network, then we can predict what is the most possible word, what is the most possible target word. So in this case, we can get the patriots. So we need to make some kind of training data before we do with this one. There is another representation, we call it GLOB. GLOB is global factors for word representation. GLOB. It is an unsupervised learning algorithm that generates factor representation or embedding of words. So the GLOB will give you a kind of probability, something like this. I want to know the probability of K. K is any word in the column given the word ice. So if the K is solid, so I want to know the probability of solid given the word ice. So we have this number. I want to know if K equals to gas. So how big is the probability given by the word ice? I want to know if the K equals to water, K equals to water given by the word ice. And if the word is fission for K, so what is the probability given the word ice? So this is the probability of this. And we can also have the K given the word steam. So K given the word steams, it means if the word is solid, so if it is followed with steam, what is the probability? And so on. Then we can make a kind of ratio, we call it this is ratio, when the probability K given ice divided by the probability of K given steam. So this is the result. And the probability of K given ice divided by K given steam when the K equals to gas, this is the result. So based on the glove representation, when it is very small or if it is very large, then solid is related to ice but not steam. Solid is related to ice but not steam. What about if it is very small? If it is very small, so gas is related to steam, but not ice. So that's the meaning when the number is very small or very large. But there is also a ratio when the number is close to 1. If the number is close to 1, it means this water. Water is highly related to ice and steam. So the word water is highly related to ice and steam because it is near 0. But this one is near 0, but it is less than 0. So the fashion is not related to ice or steam. So if it is higher than 0, then yeah, it is highly related. If it is lower than 0, it is not related. So with this kind of things, yeah, we can understand how importance of those words with another words. So using this kind of probability, we can have the glove as a word representation. There is another kind of word representation again, and it is developed by the Facebook AI research. They use the FastText. So FastText is an open source. It is free library from the Facebook for the learning word embedding and word classification. So this model allows creating the unsupervised learning and supervised learning algorithm for obtaining the word representation or the factor representation for words. So for the first text, you can use the word factors and it holds the extra information about their subwords. Subwords means something in the between of the word. For example, I have the word eating. Okay, I have the word eating. So the word eating, it can be created in any kind of characters, or we call it subwords. We can have it. We can have maybe another is ing. or we can have the word EA, or we can have the word ATI, or we can have the word TIN. So this is the subwords. And based on these subwords, we can create what is the most possible next words. So it allows for capturing the meaning of suffix or prefix for the given words in a corpus. So if you already remember, suffix and prefix. Pre means the beginning of a word. Suffix is the ending of the words. It allows for generating better word embedding for different or rare words as well. So if there is a very rare words or less frequent words, yeah, it is also where you have a high possibility for the FastText. And it also can generate word embedding for out of vocabulary words or the OOV words, because they use somehow with the representation is on the neural network. So let's just go to the Google Colab. I will not explain the mathematical behind of those things. So you can see in the Google Colab later, there are some parameters that we can use. So the parameters, we can use sentences. It means what are the corpus that we want to train. And then the factor size means the dimensionality of the word factors. So if there is no information, then they will just make as the default. The window size, if you want to define the window size, we can set also the window size. The minimum count, the model ignores all words with total frequency lower than this. So if you have the minimum count as 5, then if the frequency is less than 5, it will be big. Workers. So use these many worker threads to train the model. So if you have a good computer, okay, then you can use the workers more than one. So it can be like parallel computing. So SG. So it is the training algorithm. If you use the skip gram, then you can use the SG equals to 1. If the SG equals to 0, then it will refer to the CBOW. And we can also define the epoch, number of iteration over the corpus, and we can also the SID. So this is a kind of indexing in the computer when you run the model, so you can have the same result. So this is all that we learned. Now let's see the So in this case, I'm using the CanSim. So it is very easy to use the CanSim, and it is based on the word-to-vec architecture. And let's say the corpus is like this one. We already separate every of the word. So you can see here, this is a collection of the words, and this is I, comma love, comma this, comma movie. So I already separate each of the word. So using the skip gram model means we use the word to fact, and the sentence is the corpus. So we already split each of the word. And the minimum count. The minimum count means we will just select the words which has the frequency equals to 1. And SG means the skip gram. So if it is equals to 1, then it is skip gram. If it is 0, then it is CBOW. And then okay, let's print the factor. So if you can see here, there are factors for the word movie. I love this movie. This movie is terrible movie. The plot is confusing. So I have the factor for movie. I have the factor representation of the confusing. I have the factor of plot and so on. Okay, so we have all the factors for each word where the frequency is minimum 1. Now, if I want to know only the factor of the movie, yeah, we use the model and we use the WV to get the factor of movie. So this is the factor of the word movie that they generated with the model. And let's say I want to see the similarity between the word movie and this. So if you can see the co-occurrence matrix that we already have before. So actually we can also represent with this probability. So with the skipgram, they calculate the word movie and this, the probability is 0.09. And you can also look at the most similar with the word movie. So the most similar the word movie, we have I, which has the probability 0.2. This is the probability, love, this is the probability, and so on. If we use the CBOW model, we just use the same. The sentence is the corpus, and then the minimum count is 1, and the skip gram is 0. So the skip gram 0 means the CBOW. And then the same as the previous one, we can get another factor. Okay. So the idea is the same with the skip gram, but there is only the difference on the algorithm. So let's say I want to make another kind of data. I have this corpus. Okay. The sky is blue and beautiful. Love this blue and beautiful sky. The quick brown fox jumps over the lazy dog. A king's breakfast has sausage, ham, bacon, eggs, toast, and beans, and so on. So this is the corpus that I have. Now, you know how we do the text preprocessing. So we are using the stop words, and then we can remove some of the unnecessary words. Here, I already teach you how to make it as the lowercase, remove the special character, remove the white space. We can use the regular expression. So we just want to maintain the characters and then make the lower and then strip, remove the white space, and then we tokenize the words. And then just use the tokens that it is necessary or important, and then make it as a factor. So this is the result after we normalize. So we have the sky blue beautiful, love blue beautiful sky, and so on. After we do this one, we can do tokenize, and the tokenize will make each of this word into a list. So sky, blue, and beautiful, love, blue, beautiful sky, and so on. Again, I put this one into the skip gram. So we can use the similar. The most similar to the sky is jump, and we have this probability. Next is M, this is the probability, and so on. If we use the CBOW, we just change the SG into 0. Okay, let's just make the minimum count equals to 1, and this is the most similar words to the sky. Okay, the time is Okay, I will continue the glove and the FastText in the next class. Okay, any comments or questions? And okay, I will stop the class here and we will meet again next week on Tuesday. Thank you very much for attending class.